All right, today we are diving into one of the wildest and, frankly, coolest ideas for how we might get to space without needing a gigantic rocket. It's called the Skyhook. Now, I know it sounds like something straight out of a sci-fi novel, but it's actually based on some very real, very fascinating physics. So let's get into it. To really get why we'd even think about building something as crazy as a Skyhook, you gotta ask yourself, why is getting to space so ridiculously hard? Seriously, picture this. Imagine trying to jump, but you have to carry a backpack with all the energy you'll ever need for that jump. Oh, and then you need a second backpack just to carry the first one. You can see how this gets out of hand really, really fast.
And that's exactly the problem with rockets. It's what engineers call the tyranny of the rocket equation. The vast majority of a rocket's weight, it's not the payload, it's not the astronauts, it's fuel. And get this, most of that fuel is just there to lift more fuel. It's this vicious, exponential cycle. For every single pound you want to get into orbit, you need many, many more pounds of propellant. It's a brute force solution, and it is just incredibly inefficient.
So, what if we could cheat the system, right? What if instead of fighting gravity every single inch of the way up, we could just, grab onto a ladder and get a lift? Well, this is where the Skyhook comes in. It's an elegant, almost revolutionary idea that's the complete opposite of just building a bigger rocket.
So what is this thing? Well, in the simplest terms, a skyhook is a super long, super strong cable that's orbiting the Earth. Its bottom end hangs down, dipping into the upper atmosphere, and it's moving way slower than orbital speed. This allows a smaller craft like a reusable spaceplane to just fly up, meet it, and latch on. You can almost think of it like a celestial fishing line, just dangling from orbit, waiting to pull us up.
That sounds pretty amazing, but how does it actually fling things into space? Because this isn't just some static rope hanging there. Nope. The most promising designs involve a rotating system, which transforms the entire thing into a mind-blowing orbital slingshot.
Okay, so here's the play-by-play. The Skyhook is spinning end over end like a giant bolo in space. As one end swings down, its tip slows right down and dips into the atmosphere. A payload, maybe brought up by a jet, flies up and just hooks on. Then the hook's rotation yanks that payload upwards, accelerating it like crazy. At the very top of that arc, the payload just lets go and gets thrown into a much higher orbit, or maybe even on a path to Mars. It's literally a cosmic trebuchet.
Now, here's a really crucial point. There's no free lunch here. This isn't free energy. Every time the Skyhook throws a payload, it gives away some of its own orbital momentum, which causes its own orbit to drop just a little bit. It's like a momentum bank account. And to keep the system working, you have to make deposits to balance the withdrawals. You could do that by catching things coming down from orbit, or by using these special solar-powered tethers that can actually push against Earth's magnetic field to boost the orbit back up.
So far, this sounds like a dream come true, right? Cheap space travel, here we come. But, and this is a big but, now we have to pivot from the awesome concept to the cold, hard realities of actually building this thing. And for that, we're going to look at a detailed technical report from NASA that really lays out the monumental challenges we'd face. And here we go. Problem number one. A single sentence from a 1997 NASA report just cuts right to the heart of it. Tethers are potentially single-point structural failures. What that means is a Skyhook isn't like a bridge with lots of redundant supports. If that one tether breaks, the entire system fails, catastrophically. There's no backup. And that is an immense engineering risk to overcome.
So what could break that tether? Well, space isn't empty, not at all. It's basically a shooting gallery. And as this NASA chart shows, a tether that's hundreds of kilometers long is just a massive target for a constant storm of micrometeoroids and orbital debris. And you can see, the smaller the particle, the more of them there are, and they're all zipping around at hypervelocity speeds. We're talking about microscopic bullets here.
And just look at these speeds. A natural meteorite hits you at an average of 19 kilometers per second. A piece of man-made junk, like a fleck of paint from an old satellite, hits you at 10 kilometers per second. At those velocities, even something absolutely tiny has enough energy to sever a tether. This isn't just a remote possibility. It's a statistical certainty over time unless the tether can somehow survive it. But wait, there is more. The shooting gallery is just the beginning. The NASA report lists a whole ton of other brutal environmental problems. In low Earth orbit, you've got this corrosive atomic oxygen that just eats away at materials. You have insane temperature swings causing the tether to expand and contract. There's intense radiation, and even these complex wobbles they call skip rope motion. The point is, it's not just one problem you have to solve, it's a dozen of them all happening at once. And because of all those risks, the safety standards have to be unbelievably high.
This chart really puts it in perspective. For any mission where a tether breaking could put a crew in danger, the system needs to have less than a 1 in a million chance of failure. That means a 99.9999% success rate. Trying to engineer something this new and this exposed to that level of certainty, well, that is just a staggering challenge. Okay, so let's bring this all together. On one side, we have this incredible dream of a celestial slingshot. But on the other, we have the daunting reality of the engineering and the sheer hostility of the space environment. So, how do we weigh these two sides against each other? Look at this comparison. On one hand, the dream is absolutely transformative. Cheap, routine access to orbit. A reusable, energy-efficient system that could literally sling payloads to other planets. But then you look at the other side. The reality is a single point of failure that's under constant assault from debris and radiation, and it has to be built with materials that can withstand conditions we can barely even replicate here on Earth. It is the ultimate high-risk, high-reward scenario.
And that really leaves us with the final question, doesn't it? The dream of a Skyhook is immense. It would be a true game changer for humanity's future in space. But the challenges? They are just as big. So are we looking at an impossible engineering fantasy? Something that's just destined to stay on the drawing board forever? Or, with new materials and new ideas, could this actually be the next giant leap that truly opens up the solar system for all of us? What do you think?